hours in AC than you did with DC. Okay. All circuit solving skills that worked in DC will work in AC. Nothing changes. So you really don't have to do a lot of work in this, except RLC must have units in ohms. That's the only big deal. You turn the voltage and the currents into phasors, an RMS phasor, and you work the problem. Make sure RL and C are all in ohms. So let's look at the impedance. So basically what you have, here's a graph I'm fixing to show you of R plus or minus JX. And I'm going to tell you right now that typically if you have an RLC network, it's going to reduce to one of three types of network. I have an RLC network. It's going to reduce to three networks. And the three networks are purely resistive network. And the reason that is that the inductor, or the inductance in the circuit, cancels out the capacitance in the circuit. Because remember, capacitance is minus JXC, inductance is JXL, so when you add those two together, they will cancel each other. The second one is you can have an R plus JXL circuit. In other words, the inductor or the inductance in the network dominated the capacitance in the network and canceled it all out. And then the other type of network you can have is an R minus JXC network, which means that the capacitor dominated the inductor and canceled it out. Okay, so if you look at the graph of impedance, and I don't know if I can get all this on here. We'll see. Maybe I was a little big on this one. Anyway, the red line is XL on the imaginary axis. It's positive JXL. That's an inductor. The black line is the resistor value. It's always real. It cannot be anything else. The resistor is a real value. There's no J's involved with it. And then XC, the capacitor is going to always be minus J, and it's on the bottom. So once again, I have the three types of networks. I can have a purely resistive network because then the inductor and the capacitor canceled each other out, and all I have is a resistor network. On the other hand, I can have a resistor and an inductor network somewhere between 0 degrees and 90 degrees. Remember, we're looking at RLC networks. If it was strictly LC network, then it would be either purely capacitive or purely inductive, depending on which one canceled out the other or which one dominated. But in this case, we're strictly going to talk about RLC networks because that's all the networks there are in real power. Anyway, you have an R, and you can go from slightly less or slightly more than 0 degrees all the way to plus 90 degrees, slightly less than plus 90 degrees, and you'll have an impedance network of R plus or minus JXL. And we call this a lagging network, and I will get more into that in the next lecture. On the other hand, you could also have a purely resistive network, or you could have a capacitor impedance and a resistor. So this would be an R minus JXC network, and it can be anywhere slightly less than 0 degrees all the way to slightly greater than minus 90 degrees. And that's called a leading power factor network. Okay, so again, this is the impedance network. You have a positive JXL, you have a negative JXC, and the resistor is a real value. And as far as I know, we at least right now, we will not be studying anything other than an RLC network in this class, just because I'm more of a power guy. So anyway, once again, rehash this stuff. If I have an RLC network, it's going to reduce to one of the following. Purely resistive, in which case the inductance and the capacitance canceled each other out. I can have a Z with an R plus JXL network. In other words, the inductor dominated the circuit. Or I could have a Z, an impedance network with an R minus JXC network. And that means that the capacitance dominated the inductance. So again, in an RLC network, I can only have one of those three. So I have a unity power factor network. I have a lagging power factor network, and most networks, almost all networks that I know of, are lagging power factor. Or I can have a leading power factor network. And we'll get into power factor a little bit. I'm just kind of getting you used to the idea of power factor because it's going to be an important part of the rest of the semester. Okay, so I'm going to run through an example. I think the first homework problem is like this. This is not as easy as the one for homework. And then the other one, everything's in ohms, so all you got to do is reduce it to an ohm value. But this one, I have henries, I have capacitors, and I have inductors. So I have two inductors, some resistors in here all interspersed. Notice that I have a node up top and one big node in the bottom. And basically what this says is find ZEQ if the frequency is 60 hertz. So what I have to do is I'm going to go back and I'm going to look at those equations to turn capacitors and inductors into ohm values. So those are the two equations I need. To get an XC value into ohms, a capacitor into ohms, minus J 1 over 2 pi FC, or if you prefer, 1 divided by J omega C. They're the same. Omega is 2 pi F. To get an inductor into an ohm value, it's going to be J times 2 pi F times L, or J omega L, however you look at it. And I will say that for the most part in this class, we'll be looking at frequencies at 60 hertz, but there are book problems that the frequencies will be different, so keep up with that, okay? So anyway, typical power problem, frequency is 60 hertz. So the first thing I have to do is I'm going to change this capacitor and this capacitor into an ohm value. So here we go. So I've got to turn that value, that XC value, into ohms. So 1 divided by J times 2 times pi times the frequency, 2 pi F, or omega if you prefer, times the capacitor value, which is 2653 microfarads. Bring the J up, it becomes minus J, just some math. You should know how to do this, math. Although my math sucks. I don't know about y'all's, but I know my math does. Anyway, 1 divided by 377, 2 pi 60, 377 times 2653 microfarads. I get minus J1 ohm. Okay? So everywhere I have a capacitor in that circuit, I'm going to turn it into minus J1 ohm. So this is going to be minus J1 ohm, and this is going to be minus J1 ohm. Notice that the resistors, all four of those resistors are already in ohms, so I don't have to do anything because resistors are in ohms. Okay, next I need to change the inductors into ohm values. Once again, J times 2 pi F, which is in this case 60, times 5.3 millihenries, which equals J times 2 pi 60 is 377, times 5.3 millihenries, and I get this to equal J2 ohms. So now I redraw the circuit. I'm going to expand the top node. I'm going to bring the capacitor over onto this branch over here, and this circuit right here will all be in parallel. So here it is. Actually, if you want to get technical, it's that circuit will be in parallel. Okay, so here we go. So I redraw the circuit, and here it is. I'm looking for ZEQ. Looking into the node, I expanded that top node out and put that capacitor over here on the side, minus J1 ohm. The inductor was J2 ohms. Not that you can read that very well, but that's J2 ohms. I'll have to get a little better at this. Then I have the resistor in parallel, which is 2 ohms. I have the other capacitor, minus J1 ohm, the 2 ohm resistor, the 1 ohm resistor, the J2 ohm inductor, and then the final 2 ohm resistor. So the first thing I do, I'm going to slide this over a little bit. I'm going to add these two together because they're in series. So here we go, Z1. Z1 equals minus J1 for the capacitor, plus the J2 ohm for the inductor, and I get J1 ohm. Notice that the inductor dominated the capacitor network, and I got a positive J1 ohm for this branch over here. Well, now I have the 2 ohm, the minus J1 ohm, the 2 ohm, plus the J1 ohm all in parallel. Okay, so let's solve for that. Here we go, ZT. I have Z1 in parallel with the 2 ohm, which is in parallel with the capacitor, which is in parallel with this 2 ohm, and I add all that stuff up, and, well, not add it up, but I do the parallel thing, and I get 1 ohm. Notice, in this case, that the capacitor and the inductor cancel each other out, and I have a purely resistive network. All right? Now, once I do that, I have this other 1 ohm resistor up here that will now be in series with this combination and that 1 ohm resistor. So 1 ohm plus 1 ohm will give me 2 ohms. So Z3 becomes 1 ohm plus 1 ohm equals 2 ohms. All right? So now then, I have the inductor back in the picture. I've got this 2 ohm resistor is in parallel with the J2 ohm inductor. So Z4 then will be 2 ohms in parallel with the J2 ohms, and I get 1 plus J1 ohm for Z4. And then the final value is the 2 ohm resistor. It's in series with this stuff over here. This stuff is now a 1 plus J1 resistor. I add the 2 ohms to it. ZEQ is Z4 plus 2 ohms, which equals 3 plus J1 ohms. So if you have questions, email me. I shall put these videos up online today, this afternoon, on my YouTube account. I will also post where you can find them both on Canvas and in send you an email so you can't miss them. And please give me your comments, although I don't think at this point in time I'm going to change. I might change it a little bit. I might go to something like Camista or something like that. But this is kind of how I'm thinking about doing it. If you have comments, please let me know. And if you're in my class, send me an email to my Canvas account, and I'll get back with you for any questions.